Okay, our next test is the ratio test, and it's a very powerful test. And you can actually determine absolute convergence with this test. So suppose I have a series and I want to use this test. This applies to series that have both positive and negative terms, so we're not restricted to just series with positive terms anymore. And the first thing we do is take this limit. The limit as n goes to infinity of the absolute value of the n plus 1th term divided by the nth term. So we're looking at what happens to the quotients of consecutive terms as n goes to infinity. And if that L is less than 1, if that limit exists and it's less than 1, it might be 0, or anything less than 1, then the series converges absolutely. And of course that means it also converges. And if it ends up that that limit is something bigger than 1, or maybe infinity, then the series diverges. And if the limit is actually equal to 1, then our test is inconclusive. So let's give it a shot for this first series. What do I have to do to check whether the series converges or diverges using the ratio test? Well, first of all, we have the nth term of the series here is minus 1 to the n minus 1 times 2 to the n over n factorial. And our test says that I must calculate the limit as n goes to infinity of the quotient of the n plus 1th term over the nth term. Now, how do I find the n plus 1th term here? Well, it's actually quite easy. I just take this formula for the nth term in terms of n, and everywhere I see an n, I replace it by n plus 1. So I get the n plus 1th term is minus 1 to the n plus 1 minus 1 times 2 to the n plus 1 over n plus 1 factorial. And now the limit I have to calculate is the limit as n goes to infinity of the absolute value of the n plus 1th term over the nth term. And once I've written down that formula, the rest are details. So I fill in the details. I need to calculate the limit as n goes to infinity of the absolute value of this minus 1 to the n plus 1 minus 1, those plus and minus 1's cancel, so it's minus 1 to the n times 2 to the n plus 1 over n plus 1 factorial. That's the an plus 1 part, and now I divide that by an, which is minus 1 to the n minus 1 times 2 to the n over n factorial. Okay, I'm going to have a lot of cancellation here, and the first thing I can do is just disregard these minus 1 to the n's, because I'm taking absolute values here, so they can have no influence on the absolute value. They're either plus or minus 1, but they disappear with the absolute value. So this is equal to the limit as n goes to infinity, just disregarding the minus 1 to the n's, I have 2 to the n plus 1 over n plus 1 factorial, and it's divided by 2 to the n over n factorial. So I can invert this fraction, and I get n factorial over 2 to the n. Now, this is equal to the limit as n goes to infinity of the absolute value, but everything here is positive, so I could just disregard this absolute value from now on, of 2 to the n times 2, because 2 to the n plus 1 is 2 to the n times 2, over n plus 1 factorial. Now recall that n plus 1 factorial is n plus 1 times n minus 1 all the way down to 1, So it's n plus 1 times n factorial. And now I have n factorial over 2 to the n. And now you see the cancellation. So the n factorial cancels with that. 2 to the n cancels with that. And I'm left with the limit as n goes to infinity of the absolute value, but the absolute value is irrelevant here. It's 2 over n plus 1. And as n goes to infinity, that thing goes to 0. So that's my L. And in our test, the first, if I follow the directions, I calculate this L. And then secondly, I look at the value of L. And I have L equals 0 here. And the directions are, if L is less than 1, then the series converges absolutely. So my conclusion here is, this implies that the series converges absolutely. And of course, when something converges absolutely, that means it converges.